Welcome to the Clima podcasts. In this episode, I talk to the father of WUFI, Hartwig Künzel. Hartwig grew up on the test field of the Fraunhofer Institute, where his father worked as a physicist. Instead of following in his footsteps, he went on to study chemical engineering, hoping it would give him a broad background and so that he could travel the world. Little did he know the profound effect that he would have on the future of building science. Clima inspires and educates people to create healthy, durable and energy-efficient buildings to live, learn, work and play in. Hi there, Hartwig. Welcome to the Clima podcast. How are you doing today?
Thank you. I'm doing fine. And thank you for having me.
It's a real pleasure and an honor to have you as a guest here today, Hartwig. Now, I believe that you attended Joe Sturbeck's summer camp this year. Can you tell me about some of the presentations that you found most interesting?
Well, I had the first talk about lessons learned from 70 years of test field investigations. We have a large test field. We'll talk about this later here. That was followed by a talk from Brian Hubbs. Brian Hubbs is the H in RDH, which you might know, a large consulting company in Canada. And he talked about a case where that was pretty contentious, where a lot of money was involved, and they did WUFI simulations. And to back that up, they also had a small test hut built exactly at the location where the problems occurred to show or to prove that the WUFI simulations are correct. And we will get to this discussion later on that you can calculate almost anything and get the results you want. But if you have a field test backing that up, then it's quite reliable. There were some other interesting talks. One was from Foster Lyons on adhesion. So he explained the physics behind adhesion because we use more and more adhesive tapes and other things like that in the building practice nowadays. And he also showed what can make that adhesion or age that adhesion over time. Like moisture, for instance, is a molecule that can really degrade adhesion. That was quite interesting. Then we had a talk from Tessa Bradley, not being passive about passive house. They had an example that they showed there. The subject of passive house always turns up at the summer camp, which I think is good, because it's important to have very energy efficient buildings. I also liked the talk from Mark Rosenbaum. He talked about thermal energy storage in high performance buildings, and energy storage, thermal energy storage becomes also very important in Germany because we have to store our energy, especially we have a lot of renewable energy, and this is going up, and I think probably the country one of the countries that has a lot of renewable energy. And at wintertime, solar energy doesn't help that much. The sun is not shining long enough. So wind energy becomes important. But wind energy is not available all the time. Therefore, it's good to have energy that you can store in a house over a couple of days, up to a week. So then you need high performance building and also storage capacities that can be in the walls and the ceilings. It can also be high temperature storage, water tanks. Therefore, I thought this was interesting. And then there was a talk about load-based testing of heat pumps. I think this was also very interesting for me because we all know that it depends on at what time you run the heat pump. And of course, it's better to run it when it's warm outside in the wintertime. But you probably need it early in the morning, but it's still cold, the heat. So also there, storage can help. I think these were the most important talks. There were some others about passive houses and the shifting energy landscape and saving affordable homes and things like that. And I think those different aspects that he's always showing at the summer camps make it worthwhile attending.
Now, just looking back in your life, tell me, what was it that inspired you to study chemical engineering?
My father is a physicist and he worked already here in the institute, but I didn't really want to do the same thing in the beginning. I was familiar with that. I grew up at the test field here. So I thought I wanted to do something else, but I was sure that I was like math and physics. So I thought engineering would be good. And chemical engineering appeared to be very broad because you have chemistry, you have engineering, and also the possibility to go abroad because at that time, the big companies like Bayer, BASF, and so on in Germany who employed chemical engineers also had a lot of subsidiaries in other countries. So that was the reason why I started to study chemical engineering.
Did you ever imagine the profound impact that you would have on the future of building science?
Not really. This was not my intention. When I started here at the institute, my father was still here, but I started in another department that was mainly dealing with moisture control of heritage buildings. I thought heritage buildings were very fascinating, and that was the reason why I started to work here. Then my former boss had a model, but that was pretty cumbersome. It was hard to make it converge and things like that, and we didn't have the material properties. So I tried to develop a new model from scratch that used only very simple parameters that were easy to measure, that we usually had already, like vapor diffusion resistance and things like that, liquid diffusivity and so on. And that's all we needed for this model. And during my work at the university, I got deeply involved into computational fluid dynamics, so CFD. So my bachelor thesis I did at UMIST, the University of Manchester, Institute of Science and Technology, and I learned a lot there. And the master thesis I did at the École Centrale in Paris, and also used the CFD models there. So I had these CFD models already at hand, and then I changed them to do also moisture calculations.
Other than your boss's modeling tool, what methods were used for hygrothermal modeling prior to WUFI?
In practice, they mainly use the dew point method, which has a lot of limitations and is not really recommended anymore. Even the ASHRAE Handbook of Fundamentals says it doesn't recommend dew point method as the sole method to design moisture control or something like that for buildings, for moisture control design. And we all knew that we needed something else. Of course, there was also a lot of practical experience, long track records of different building assemblies. But once we started to insulate our buildings and to make them more airtight, that proved to be a game changer. So many of the well-proven and building assemblies didn't do that well anymore once they were insulated, because then the outside became colder, the inside became more humid because now the building was more airtight. We had higher vapor pressure gradients, and that caused problems even in constructions where we would never have expected that. Also, the practical experience was not so helpful after we heavily insulated our buildings. And that's one of the reasons why these hygrothermal simulation models were developed during that time, and also because with the Glaser method or the dew point method, you could just look at vapor diffusion, but also wind-driven rain was a problem. That was a high load, and you couldn't deal with that at all.
If someone is wanting to start using WUFI and they visit the website, there are a number of options that they can choose. Where would you recommend that they start?
Well, I would always recommend them to start with the one-dimensional version of WUFI before they go two-dimensional or the whole building hygrothermal simulation tool. And then I think they first need quite a bit of information before they start. attending a WUFI course would be a good idea. And you are doing this in New Zealand and Australia. We are doing this in Germany. Our partners worldwide, also in the United States, we have training courses on a regular basis. So I think it's a good idea if you do that, unless you have somebody who knows WUFI very well and can teach you in your office, then this is also a good thing. And once you have done such a training course, it's always good to use WUFI on a regular basis. If you use it only once a year, it's probably better to let somebody else do the simulations. Then this is probably more reliable. So training is important, but also a practical background, I think, is important. So you have to check your results for plausibility. And that is easier if you have an idea on what's really going on in practice.
Here in New Zealand, when new users start using WUFI, we often get asked the question, how do they create a WUFI model when a lot of the local products are not available in the system?
First of all, I believe that the products in New Zealand are not that much different from the ones that we are using in Europe or the United States. Therefore, you could start to use these properties. If you're unsure, what you can always do is you can do a parametric study. That means you change the material properties in either way a little bit, by 10 or 20% or something like that, of all individual layers. And then you will find out which ones are really important. You will probably find that the most important layers are vapor retarder and maybe water-resistive barriers and things like that. Everything in between has some influence, but usually not a lot. So therefore, to use material data that are generic is in many cases good enough.
You mentioned the importance of vapor retarders. Can you tell us more about the significance of understanding the vapor permeabilities of the layers in our construction?
The vapor permeability is still the most important property that we have, because even though you sometimes have a liquid flow and things like that, wind-driven rain and so on, most of the water will then dry out again by vapor diffusion. And therefore, the vapor permeability is probably the most important parameter when it comes to hygrothermal simulations. The good thing about that is that it's mostly pretty well known. At least for European products, you need to have that vapor permeability. And you always needed that also for the dew point calculations. Vapor permeability was the only very important parameter besides thermal conductivity, but that's also usually well known.
So can you tell me, who was it that invented vapor variable membranes?
Well, without boasting, that's me. If you want to know how that came about, there were several reasons. We had Tudor houses. We built up a Tudor house at our institute, and Tudor houses can only be insulated from the inside because you want to have that appearance on the outside of the facade. So if you insulate them on the inside, you have to protect them from vapor diffusion from the indoor air. At the same time, in wintertime, in the same time, in summertime, you have a problem with wind-driven rain. So it would be good if that water could also dry towards the interior. And that would mean it would be good to have a vapor retarder in wintertime and no vapor retarder at all in summertime. But that's pretty complicated to do. We did a field investigation for Clima, where we had the old pitched roofs in Germany where had a under roof, which was wooden sheathing and bituminous felt on top of that. So pretty vapor tight towards the outside. And then they were filled with cellulose fiber. And then you could also use a vapor barrier, but then you had always the risk when some water got in that it didn't dry out again. And therefore, at that time, Clima started to produce vapor retarders that had maybe 1 perm of permeance. I don't know how that translates in the units that you're used to, but it was a craft paper, basically, yeah? And a little bit more vapor retarding than normal craft paper, and that's all. So we did that field test, and did also WUFI simulations to compare it. Because it's always good if you have a field test, and then if you have validated the simulations, then you can also do extrapolations and can use other climates, indoor or outdoor, and see how the whole system would work there. So we had a perfect fit during wintertime, very good agreement between measurement and calculation of the wood moisture there in the roof at the sheathing. And when the summer started, or spring after springtime, then the both curves diverged. So in the field test, the water dried out much faster than in the simulation. So I thought that was strange because I was quite confident that our model works well. We did a lot of validations before. And then what I did is I lowered the thermal resistance, or I increased the permeance of the kraft paper only for the summer period. And suddenly I had a very good fit again. I said, okay, that's interesting. So what we would need actually is a vapor retarder that is less permeable in wintertime than it is in summertime. We took samples from that, did measurements in the laboratory without Clima knowing about that. But then we were quite disappointed because that was an irreversible process. So the kraft paper did not get back to the original permeance under the conditions of wintertime. And when you do a WUFI simulation, that's a good thing about it. You see exactly what climate conditions or microclimate is facing that vapor retarder. So you see on the room side and on the other side exactly what is the relative humidity. And I figured out immediately that it was pretty dry in wintertime. We had about 40% indoor humidity. And on the other side, it's even less because the vapor pressure is controlled by the coldest temperature in the roof. And therefore, you had there maybe 20% RH. So on average, 30% RH. In summertime, when the moisture flow came from the sheathing towards the interior, we had about 70-80% RH. So if I had a material that changes the permeance with the relative humidity, then that would be such an ideal thing. And I did WUFI simulations in order to find out what would be a good material, what properties it should have. And then I applied for a patent. Then I got some feedback to that from patent office. And they said, okay, yeah, that's interesting. But what is the material? I said, I don't know. I just know the specifics of that material. I don't have the material yet. Well, if you don't have a material, you cannot file a patent. So we were looking for material. I knew that some polymers had this effect that when it was more humid, that they had less permeance, were more permeable. And therefore, we checked a lot of different materials and we came across polyamide or nylon film, and that had exactly the properties that we required. So we were quite lucky there. And that was the beginning of that, what we call smart vapor retarder or humidity controlled vapor retarder.
What are some of the most surprising results that have come out of WUFI modeling?
I don't know, was surprising for me in the beginning. There was a bit of a nuisance when the supervisor of my PhD thesis saw all my validation cases and things like that. He said, yeah, well, but there's an old validation case that was a autoclave rated concrete roof that didn't have a vapor retarder. And when you do dew point calculation, that wouldn't work. But the company didn't want to install a vapor retarder at that time. That was in the 60s, because they had a high initial moisture content from the production in the autoclave rated concrete slabs, and that was required to dry out towards the interior. And they said, well, that works well. We have practical experience, and we don't need a vapor retarder. Vapor retarder would be counterproductive. And therefore, we did test for that. And my former boss, and with this model, he could calculate this perfectly, had a very good fit between his simulations and the experiment. And when I did this using the old climate data from that time, but they were only available in daily mean values, then it didn't fit. So I thought, well, what is the reason? Why doesn't it work anymore? I was so confident that my model worked, and then now I got results that showed, well, just doesn't dry out fast enough and things like that. It's not the same thing. And then I looked at all the data, climate data again. I thought, okay, if you have daily means for radiation, for temperature, that's getting pretty low, considering that the saturation vapor pressure is increasing with temperature exponentially. I thought, well, maybe it's not good to have these daily mean values. That doesn't work. And I just took, because our filter site is always here and we have a meteorological station now, we have, since the 80s, we have hourly values. I used those and then I got a perfect fit again. So that was surprising that hygrothermal simulations need hourly data. If you do it with daily means, and then I also looked at monthly means, there's not a big difference anymore whether you use daily or monthly means. But going from daily to hourly, that makes a big difference due to that exponential rise of the saturation pressure. So that was quite surprising. Another thing was we were involved a lot with natural stones during our heritage projects because natural stones degraded over time. And the question was, what was the reason? What can we do about it? Does it help to treat them with water repellent chemicals, or what can be done about it? And therefore, we did also a lot of simulations. And when we did a simulation over several years, and then we had the dynamic equilibrium, and I compared the mean temperature and moisture distribution, I was surprised because if you look at the temperature distribution, it's always a straight line from the interior to the exterior. If you look at the moisture distribution, the water content distribution, you have very low values on either side, interior and exterior, and then pretty close to the exterior surface, then the average water content peaks. It's much higher than at the exterior surface. So I thought that's surprising. Can that be true? So we did a lot of NMR scans of our samples that we had, and we found out, yeah, it's true. And that was surprising in the beginning, but it explains a lot of things because quite often the zone just beneath the exterior surface is the one that's degraded the most. That leads to delamination or to spalling and things like that. And now we could explain why that is, because that's the zone where we had the highest water content on average. That's also the zone where you'll find frost damage. That was quite interesting to realize. Another interesting thing was, I think once we had the model and it was established, we used it every time we did a field test. We use the model because when you do a field test, you monitor temperature, relative humidity, sometimes water content, wood moisture. And we had the climate data because we have a meteorological station here at our institute. So it was the easy task to do a simulation and to compare the results. And most of the time, well, it was pretty good. And we had quite a few times where it didn't fit. And about 90% of these times, it was an experimental error and not an error of the simulations. So that's interesting to note. I wouldn't have expected that either. But nowadays, the simulation are, if you have the right input data, are so reliable that you can even check on the experimental results.
So, Hartwig, are there any really challenging climates that you've come across when calculating a WUFI model?
Hot and humid would be one, and very cold also. But also top of the mountains, deep in a valley, that's challenging because, of course, you usually have data from near the airport or somewhere else, but rarely top of the mountain. But you can calculate what will go there. If you have models that can calculate the microclimate for microclimate conditions that will help in this respect. Also, shading is an important factor because for drying of materials, we also rely a lot on the sun, and especially on the west or the side where we get all the drying rain from, it's important to have enough radiation. And therefore, shading may be an issue that may be challenging. From my experience, it was also interesting to look at frost damage in different parts of Germany and also compare that to what happens in Canada and the United States. And it was interesting that it's not the cold temperature alone that's important. It's the freeze and thaw cycles. Moderately cold climate zones show more frost damage because you have more frequent cycling. And this is also something where we try to create a post-process model for freeze and thaw cycles in order to predict frost damage. That's an interesting thing. When it comes to maritime climate, you have the salt impact. So quite often you find salt in the building materials, and it also changes the properties. What's also very important and still is challenging is the question, how are the material properties changing over time by aging? Because what you find in WUFI and in all databases now of all simulation tools are the initial material properties that were measured before the material was installed. And now the question is, how is this changing over time? I think we have the opportunity that we have a lot of buildings that have been here since the beginning, so that we can monitor for 70 years and could take samples to see what happened to the materials. And I think that's interesting. Sooner or later, we have to deal with that. And another aspect that's interesting, and we did some simulations about that, is the topic of climate change. How does that affect our buildings? And for that, we need meteorological data for the future, which there are already some models around that you could use, and then to find out, because we build our buildings for the future and not only for today. And therefore, it might be interesting to switch from the meteorological data that we're using today to those that we will have also in the future.
So, Hartwig, what are some of the challenges that you're facing and the new things that you're developing at WUFI at the moment?
This question of storage, energy storage, thermal energy storage, is something where we did quite a bit of investigations together with our energy department. And energy storage we also use our WUFI Plus, our hygrothermal whole building simulation model, because every time you store energy, then this has also an effect on moisture. And that effect becomes even greater when you store cooling energy in summertime, for instance, and try to release it. So that's one of the important issues that we are doing. And also, we work on post-processing models. We have one for mold growth. Now we have one also for rot, and we keep on developing that. We have one for corrosion of iron anchors in natural stone buildings or things like that, so from the heritage side. But now we are developing also a corrosion model for concrete, reinforcement of concrete. And that seems to be a very important subject more and more. Just yesterday, we had a bridge that collapsed in the city of Dresden in Germany, in the city center, because of corrosion, concrete corrosion. So that seems to be a very important subject that we are dealing with. Well, also, we try to make it simpler for users to use our program. That's the important thing. And we also thought about AI, so artificial intelligence, to help us with that. So these are the different approaches that we do at the moment.
Now, as a last question, Hartwig, in a podcast I had with John Straub, he was challenging the results obtained from WUFI modeling versus the results of real performance of buildings. How would you respond to that?
Okay. I know that what John is saying, John Straub, he always says the problem with hydro simulations is if you put garbage in, you get garbage out. That's true. There's no doubt about it. I think Joe Seabrook, who was called Steve Brick at last summer camp, so that was this was an old name that he used in the past and in Canada, apparently. He wrote an article that had the title, Is WUFI Barking Up the Wrong Tree? I know that both of them are highly respected, famous consultants, also expensive consultants. And when they are called, then something had or went really terribly wrong. So they see a lot of cases that don't actually work, and where people did mistakes, used the wrong input data or things like that, or tweaked them because they wanted to end up with a certain result for their clients or something like that. In practice, or we get also feedback from our users quite a lot. And there it turns out that they have much less problems that you would assume once you're an expert witness and seeing all those cases that have gone wrong. So I'm not so concerned. I'm not so pessimistic about that. Also, when we look at our standards now, especially in Germany, but also in other European countries, our moisture control standard shows you where hygrothermal simulations are required. So there are limitations that apply for the dew point calculation. Then, of course, you have those deemed to satisfied constructions. But all the other constructions, and especially if you have a different indoor climate that is different from the normal indoor climate in a residential building, then you have to do a WUFI simulation. But then there are fixed settings. So you know what settings you have to take. Well, it's not that difficult in Germany. It's one climate zone. And if you want to use other settings, then you have to explain exactly why you did it. So you need to have a good rationale behind that, then it's possible. And I think that keeps many people from making big mistakes when they are choosing the input data. And I think the more advanced models like WUFI also help the user to select input data that are reasonable. You have a choice. You cannot select something that's really stupid. Or if you insist on that, you might be doing that. But then you know you're not taking anything that was pre-selected. Then the same thing holds. Once you do that, once you take a completely different setting, then you need to have a good rationale behind that. So therefore, do we have another choice? No. How can we do it? Of course, we can do experiments, but experiments are expensive, and they can do an experiment only once you have built a building. But if you're in the design stage, you can't do that. It's impossible. The dew point calculation is not good enough, so you need something else. And of course, there are very good consultants and building scientists who can tell you, well, I have the experience and that. But most of the experience they have is limited to the climate zones where they have investigated. If you go to a completely different climate zone, it's difficult to predict what's going to happen, especially in hot and humid climates. You need to have different building assemblies. Cannot compare that to what you usually have in Europe or the United States, or even in New Zealand. It's maybe not a problem for New Zealand, but maybe for Northern Australia.
Well, thank you so much for coming on the show with me today, Hartwig, and I really hope we can catch up again sometime soon.
Thank you very much for having me, and I think that's an interesting discussion. Maybe we could have one day a discussion with maybe Joe and John together, but I don't know whether we can do it in this scope, but it would be interesting to hear their answers to my ideas and vice versa.
I agree totally, Hartwig. That would be a fantastic opportunity to have all three of you on the podcast at one time. So I'll reach out to them and see what we can do. All right, then. You have an awesome day, and bye for now.
Thank you very much.
Sharing knowledge is at the heart of our strategy to make buildings better for everyone. Sign up for our podcasts to learn more about creating healthy living conditions by protecting building structures from external and internal moisture damage. Thanks for listening. Looking forward to having you with us next time.